In this tutorial, we will examine D-value, which is a characteristic of thermal destruction of microorganisms. So if we take a homogeneous suspension of microorganisms and we heat it at a constant temperature, the microorganism destruction commonly follows a logarithmic order of death. Now we say commonly because certain variations are also observed, but those will be subject of a different tutorial. So let's make a plot of number of microorganisms per unit volume. We will give it a symbol N versus time, and we will use the symbol T. So if we plot the number of microorganisms in this unit volume when it is heated at a constant temperature, we will obtain an exponential plot as shown in this diagram. Note that this is an exponential decrease, and we also call it a survivor curve because the points on this curve represent survivors at any time when that suspension is being heated at a constant temperature. Now, to be able to obtain some useful parameters, we can convert the y-axis into log scale. Now, there are two ways of doing that. One is that we can take that number of microorganisms and take a log of that, or we can plot the data on a semi-log paper. So what we have here on the y-axis is the log scale. So we have 10, 100, 1,000, 10,000, for example, for number of microorganisms per unit volume. And if we plot that survival curve, we will notice that we get a straight line. The time required for one log cycle reduction, as we see here in this plot, is called the D-value. Note that this D-value is obtained from the x-axis where the units are of time. So D-value is called the decimal reduction time. It is the heating time in minutes at a constant temperature that will result in reducing the microorganisms by a factor of 10. So we see here in this figure that this D-value represents the time for the number of microorganisms to decrease from 1,000 to 100, or it decreased by a factor of 10. We can also say that D-value is the time for the survivor curve to traverse one log cycle. So D-value remains the same for each of the log cycles on this curve. So the reduction is by a factor of 10, as we observed before, from 1,000 to 100. If we wanted to know the percent reduction in microorganisms during one log cycle, we can take 1,000 minus 100, that is the decrease during that one log cycle, divided by the initial number of microorganisms. We had 1,000 at the start of that log cycle, times 100, and that gives us 900 over 1,000 into 100, or 90%. So there is a 90% reduction in the number of survivors going through one log cycle. And that reduction of 90% for each log cycle will remain the same along this line. We will make a few more observations. One is that the D-value remains the same for each log cycle, and D-value depends only on that 1 log cycle, because d-value is obtained from 1 log cycle reduction in the microbial population. Also note that d-value is expressed in time units, most often as minutes. And again, it is a 90% reduction in the existing microbial population. We can also observe from this figure that if we were interested to find the time required to decrease the microbial population from 10,000 to 100, then from this plot, that means that you will need to heat that suspension at that constant temperature for twice the decimal reduction time. So the process will be 2 times D. Keep this in mind when we see later in another tutorial as to how we determine thermal process times. We will also observe in later tutorials that the D value for microorganisms and for nutrients present in the food vary considerably. In fact, the D values for nutrients can be 100 to 1,000 times the D value for microorganisms. A large D value signifies that at that constant temperature, the 90% reduction will take much longer than another component in the food that may have a shorter D value. Again, we will consider these features about D value in a separate tutorial.